Discussion session for assignment 4. Question number 1. Mark the true statements. The root test and ratio tests are tests for absolute convergence. Yes, this is there in the notes. B. Neither the root test nor the ratio test can show that summation 1 by n squared converges. Yes, if you remember the proof of ratio test, there was a third case. If L equal to 1, then the ratio test cannot say anything. Well, this was the example given. Similarly, there was an exercise left for you for the root test, and I hope that you would have got that summation 1 by n squared converging cannot be shown using the ratio test either. Root test either. The root test can show convergence of summation 1 by n squared, but the ratio test cannot. Obviously, option B rules out option C. D. Neither the root test nor the ratio test can show that summation 1 by n diverges. That's an easy check. Question number 2. Which of the following are true? Every bounded sequence of real numbers has a convergent subsequence. Yes, that's just the statement of Bolzano-Weierstrass theorem. A monotone sequence of real numbers is convergent if and only if it is bounded. Yes, this is true. If it is bounded, it is convergent by the monotone convergence theorem. If the sequence is convergent, then it's automatically bounded irrespective of whether it's monotone or not. Option C, a sequence xn is convergent if and only if the sequence mod xn is. Well, if xn is convergent, then mod xn is convergent. However, if mod xn is convergent, xn need not be convergent. For instance, just look at the sequence minus 1, 1, minus 1, 1, minus 1, 1, so on. This is not a convergent sequence, but mod xn is just 1, 1, 1, 1, 1, 1, 1. So a sequence can be divergent with mod xn being convergent. Option D, every sequence has a monotone subsequence. Yes, this was the result of Newman that I had proved in the lectures. Next question. Consider the sequence an defined to be 1 by n. Mark the true statements below. Summation n equals 1 to infinity an converges. Obviously not. Summation n equals 1 to infinity sin n an squared converges. Well, summation 1 by n squared converges, and we are just adding, multiplying the term sin n whose value is between minus 1 and 1. So by comparison test, you can show that summation n equals 1 to infinity sin n an squared actually converges. The next one, an divided by minus 1 power n converges. Yes, this follows from the alternating series test. Finally, summation n equals 1 to infinity an squared converges, that you are all familiar with. Question number 4. Let xn be an increasing sequence of irrational numbers in 0, 2. Then xn converges to 2. No, that's complete nonsense. You can have a sequence of irrational numbers that are increasing, but that's not increased to 2, obviously. Xn converges to root 2. Again, this is again a nonsensical option. Options A and B are both nonsensical. You shouldn't have even considered ticking them. Option C, xn converges to some number in 0, 2. Yes, this follows from monotone convergence theorem. Xn might not be convergent. That's not possible simply because any bounded increasing sequence must definitely converge. 5. Consider the assertion, the sequence xn as a convergent subsequence. If xn are all elements of which of the following sets is the assertion always true? Close 0, open infinity. No, you can have a sequence of increasing terms like 1, 2, 3, 4, 5, 6, so on, which has no convergent subsequence. Close 0, 1. Yes, this will just follow from the Bolzano-Weierstrass theorem. Minus 1, minus half. That will also follow from Bolzano-Weierstrass theorem. 0, 1 union minus 1 minus half. This will also follow from Bolzano-Weierstrass. So this is a rather easy question that just checks your understanding of what bounded sequence means. Question number 6. Which of the following requests is possible? A sequence that has a subsequence that is bounded but contains no convergent subsequence. No, again, this is ruled out by Bolzano-Weierstrass. This assignment could have been called an assignment on the Bolzano-Weierstrass theorem. Of course, that is the most important theorem of this week's content, so that's why I've focused on Bolzano-Weierstrass theorem. B. A sequence that does not contain 0 or 1 as terms, but has subsequence that converge to each of these values. Of course, this is very easy to construct. You just construct a sequence that does not contain 0, does not contain 1, but converging to 0 and 1. I leave it to you. It's a very, very simple exercise. A sequence that contains subsequences converging to every point in the infinite set 1, half, 1 by 3, so on. Well, this is also rather easy to do. One way to do it is to consider one of the exercises in the previous week where you enumerate the rational numbers. Using that, you can actually do this. There are several ways to actually construct such sequences. One particularly interesting way would be to consider 1 minus 1 by n, one sequence, half minus 1 by n, 1 by 3 minus 1 by n, and so on. You consider these sequences and put them all together as one grand sequence, and you will be able to see that this will happen. How you put these sequences together, I leave it up to you, to your imagination. You can combine them in several ways, use the results from countability and all that. You will be able to do it quite easily. Option D, a sequence that contains subsequences converging to every point in the infinite set 1 half 1 by 3 dot dot dot, but no subsequence converging to 0. This is simply not possible. What you have to do is, we know that there is a subsequence that converges to 1, there is a subsequence that converges to half. What you do is, you create a new subsequence where the nth term of this new subsequence is nothing but the nth term of the subsequence converging to 1 by n. So please unravel what I just said. Unraveling this will make a light bulb glow in your head, and you will understand how to construct the subsequence that actually converges to 0. So this is a somewhat tricky exercise, and I do not want to spoil your fun, but the complicated statement that I just said would be more than sufficient to help you on your way to finding out the subsequence that converges to 0. So let's move on to the next page. Which of the following propositions are true? If every subsequence of a sequence converges, then the sequence converges. Obviously, because the sequence itself is a subsequence of itself. If a sequence has a divergent subsequence, then the sequence itself is divergent. That's also true. If a sequence has a divergent subsequence, that merely means that every subsequence cannot converge. That's what it really means. And we have shown that if a sequence converges, then every subsequence converges. So this is not possible. A sequence, if it has a divergent subsequence, then the sequence itself must be divergent. C, if a sequence is bounded and divergent, then there are two subsequences that converge to different limits. Yes, if a sequence is bounded, then every subsequence must have a further subsequence that converges. This is simply because of Bolzano-Weierstrass yet again. But we have also shown that if a sequence has the property that every subsequence has a further subsequence that converges to the same limit, then the sequence itself is convergent. So the only way by which a sequence can be bounded and having bounded and divergent, then the only possibility is there must be two subsequences that converge to different limits. There's no other choice. Option D, if a sequence is monotone and has a convergent subsequence, then the sequence itself is convergent. This is a very, very easy exercise. You know that because sequence is monotone and it is convergent, let's call that limit x. Then after a particular point, mod xn minus x will be less than epsilon. That's the definition of convergence. Now let's assume that this sequence is increasing. Well, that means x has to be greater than or equal to xn, and we already know that mod xn minus x is less than epsilon. So if you choose an m greater than n, xm minus x will also be less than epsilon, because xm is squeezed between xn and x. Similarly, you can argue for the case where xn is a decreasing sequence. So that concludes problem number 7. Let's look at problem number 8. Let an and bn be Cauchy sequences. Which of the following sequences are also Cauchy? Mod an minus bn. Of course, mod an minus bn will be Cauchy because an minus bn will be a convergent sequence. An and bn are Cauchy, therefore they are convergent. An minus bn will also be convergent, therefore an minus bn will be Cauchy. Therefore mod an minus bn will also be convergent, and therefore mod an minus bn will be Cauchy. Okay, that was a lot of words without a breath. Okay, option 2, minus 1 power n an. Of course, the minus 1 power n will just disappear when you take the modulus when trying to show that minus 1 power n an is actually Cauchy. A and bn, obviously an and bn are Cauchy, therefore convergent, therefore the product is convergent, therefore the product is Cauchy. Finally, box an, where box of x refers to the greatest integer less than or equal to x. Well, how can this fail to be Cauchy when an is Cauchy? Well, do the following. Look at the sequence minus 1 by n and 1 by n alternating. That is, the sequence looks like this: 1 minus half, 1 by 3 minus 1 by 4, 1 by 5 minus 1 by 6, 1 by 7 minus 1 by 8, and so on. Okay, now look at the definition. It refers to the greatest integer less than or equal to x. So when the sequence an is greater than 0, then box an will be 0. When an is negative, then box an will be minus 1, right? So because of this, the sequence box an will alternate between 0 and 1, and therefore it's not Cauchy. Question number 9. This is a somewhat tricky question. Which of the following series converges? Summation n equals 1 to infinity, 1 by 2 power n plus n. This you can show by comparison test and using the fact that 2 power n will be greater than n squared whenever n is suitably large. Options B, C and D are somewhat tricky. I'll give a handout where I will illustrate how you can show that none of these are actually convergent. Question number 10. Suppose you are given a series summation an and are asked to prove that it diverges. Which of the following ideas are good to achieve this? Show that summation mod an diverges. No, this is not a good idea because you can still have summation an to be convergent. So summation mod an diverging does not show that summation an diverges. Show that an does not converge to 0. Yes, this is a sure shot good idea. If an does not converge to 0, then definitely summation an cannot converge, and this is a standard way by which we show that series diverges. Okay, but however, I caution you, this is just a sufficient condition for divergence. It's not a necessary condition. Find a divergent series summation Bn with Bn greater than or equal to n and apply the comparison test. This looks very nice, but except the comparison test is applied in a completely wrong way in option C, so it's wrong. Apply the root or ratio test. Yes, they can show divergence. You just have to show that L is greater than 1, but the issue will arise that sometimes it may not be possible, but this is a good idea nevertheless to achieve this. So this concludes the discussion session for assignment 4. Please have a look at the handout also. Thank you.